All right, welcome back. Today we're going to talk about intermolecular forces. That's going to be sticking molecular compounds together. When you have multiple molecules, they have a tendency to stick together. And then the prefix here, inter, means between different molecules. Intermolecular forces, forces of attraction between molecules. So that force, that stickiness, we learned about bonding. That's a force that holds atoms together. These are going to be forces that hold molecules together. We can determine the strength of the intermolecular force by looking at the boiling point or the melting point of that substance. So the higher the melting point or boiling point, the higher the force. Now we have different forces for nonpolar substances compared to polar substances, or at least we can talk about the importance of those forces for those types of substances. And then it's important to note that some molecules have multiple types of forces that are occurring. So we're going to go in order of importance for affecting the melting point or boiling point as far as the strength. So this is going to be the strongest to the weakest forces. The first one would be for polar molecules, and it's going to be dipole-dipole forces. Now we have a special kind of dipole-dipole force called H-bond or hydrogen bond. This is the strongest of all the intermolecular forces, and it can only happen when hydrogen is bonded to fluorine, oxygen, or nitrogen. I call it FON because they are all next to each other on the periodic table. Now, why does this work? Hydrogen, very small atom, and it has a relatively low electronegativity when bonded to either FO or N, is going to basically give its electrons mostly towards that other atom, FO or N. And because it's so small, when it goes up against another molecule, it's able to really get in close and cause that force in between the two atoms. So this is representing the H-bond right in here. Again, this can only happen when hydrogen is stuck to FO or N. Because of this sharing, you happen to have this slightly positive end on the hydrogen, slightly negative end on the opposite. And as you can see in this picture, also on that slightly negative end is this attraction for that lone pair of electrons stuck on that other atom. So hydrogen bond, strongest intermolecular force. It's a special kind of dipole-dipole, where again, dipole two-ended molecules. So then we have just normal dipole-dipole forces, and it has to be two polar molecules. So typically what we see is, here's an example of a molecule. Is it polar or not? That's what we're looking for. And if it's polar, we can tell by looking at the net dipole, the net polarity using Lewis structures, or we can just talk about a single bond if it's a binary compound. So just to show you how this works, like let's just say we have a nonpolar substance of chlorine bonded to itself. Its melting point, or in this case boiling point, is negative 34 degrees Celsius. But if we were to switch one of those chlorines out for iodine, which is just a little bit below chlorine on the periodic table, that bond goes to 97. So this suddenly becomes a polar covalent bond. Because it's polar covalent, we now have dipole-dipole forces. So that change in one atom has a tremendous change in the boiling point. The third kind of a dipole type intermolecular force that's involving polar molecules is something called dipole-induced dipole. So what's going on here is you have to have a mixture of molecules, and one of those molecules is going to be polar, the other is going to be nonpolar. So if you're being asked a question on a quiz or on a worksheet, if you only have one substance listed, it's not going to be dipole-induced dipole. You need to have two substances listed as in a mixture. So what happens is this polar molecule comes up close to the nonpolar molecule. Notice that there's an even distribution of electrons in this picture. When this slightly negative end comes close, it's going to push the electrons in these electron clouds away because like charges repel each other. Since it's going to push those electrons away, what you end up having is an uneven distribution of electrons in the nonpolar molecule, which creates a temporary dipole. So now, because some of these electrons that were on the left-hand side get moved to the right-hand side, you have a greater concentration of electrons or negatives on the right, which creates that partially negative charge. Because this side's partially negative, by default, this has to be partially positive, and now this partially positive is going to attract this partially negative. That happening creates the dipole-induced dipole intermolecular force. This is really important as far as water and oxygen. So that's why this picture is showing water and oxygen, because this is what allows oxygen to dissolve in water, which is incredibly important for marine life. Without this happening, dipole-induced dipole, you would not be able to have fish because there wouldn't be dissolved oxygen in the water. Then the last force, and all molecules can do this, but it's really only important for nonpolar molecules, because the other forces, the dipole forces or hydrogen bonding, if present, are much more important for polar molecules as far as affecting the boiling point and melting point. London dispersion are only really important for nonpolar molecules. Now, this is a result of the consistent random motion of electrons. Electrons in a molecule or in an atom are always moving around. Now, statistically, those electrons are distributed evenly throughout that electron cloud of the atom, and then that electron cloud kind of extends into the molecule as well. But at any given moment, you might happen to have electrons that aren't equally distributed, and because of that, at any given time, there might be one end of the molecule that might be just slightly more negative. So here's like an even distribution. Here, just at the moment, these electrons happen to be more on the right-hand side. So this could be happening at any given moment. Now, if this is happening in this molecule and there happens to be a second molecule right next to it, these electrons are going to push the electrons in the second molecule's electron cloud away. And so what that happens is it's a cascade effect of electrons pushing each other around in opposing molecules, and because these electrons are moving around, there's going to be a slight positive or a slight negative charge. That slight positive or slight negative charge is the London dispersion force. That's the force that keeps those molecules attracted to each other. So there's two factors when we consider London dispersion forces. And the more important of the two is the size of the molecule. And we look at the size based on how heavy it is. It's molar mass in grams, so you just figure that out using the periodic table. Bigger molecules, by definition, should have more electrons because they have more energy levels inside of them. Because there's more electrons, they can be pushed around more often. There's just more chances for these electrons to get moved around. Because of that, the bigger the molecule should be the higher London dispersion force, and therefore the higher boiling or melting point. So, example of that. Fluorine, pretty small, it weighs 38 grams per mole. Its boiling point is negative 188. Just one row down using chlorine instead of fluorine and almost double the molar mass, you now have negative 34 degrees C. So pretty big difference in the boiling point just because you're not even quite twice as heavy. The second factor that influences London dispersion force is the length of the shape of the molecule. If you have a long straight carbon chain, what that does is it allows the molecules to pack more tightly. And if they can pack more tightly, they can influence each other to a greater extent. So these electrons, because they're packed tightly next to their neighboring molecules, are able to push those electrons in the neighbor, and then that just creates that chaining cascade effect at a greater extent. Also, the length, the longer that you are, the more distance you can push these electrons, and also the more like surface area. So it's kind of like a stickiness, if you will, between the two different molecules. So here's an example of a 4-carbon chain, butane, negative 0.5 degrees Celsius for its boiling point, whereas if you double that chain, the boiling point is tremendously higher, 125 degrees Celsius. So room temperature, this is a gas. Room temperature, this is going to be a liquid. So after this video, you should understand that there's several different types of intermolecular forces, and ranging from importance for boiling point would be hydrogen bonding, dipole-dipole forces, dipole-induced dipole, and finally London dispersion forces. Don't forget that molecules that can do hydrogen bonding can also do London dispersion forces as well. It's just that London dispersion force is not nearly as important as hydrogen bonding is for the characteristics of that substance. And finally, nonpolar substances can only do London dispersion forces, so they are influenced by these two factors. Hope that helps.